Good afternoon, everybody. I'm sorry for this delay. And okay, so I would like to remind to everybody that for this course here, the presence at the lecture, I think, is an important relevance because the course is not so easy to be taught and to be understood, okay, especially in this COVID emergency. So I recommend to attend this course whenever it's possible. And I think I realize that it's not easy to organize the time, but I think, I believe, not I think, I believe that the development of the theory together with the teacher or the teaching person and the attending or the learning person is important. Is an important process for understanding. Okay, so I see that the present person are actually only 20, and we started about an amount of person about 40. So I don't think that my level, the content of the information was modified in time, was always the same. So I recommend to attend. However, you can do, you are free, you can do what you want, but this is my recommendation at the moment. Okay. I want to develop my lecture now. And today I want to consider the key point here after after the development of the unsteady aerodynamic, now we have the following, and we want to find solution for this. In this case, this term here is a generalized external force, modal force. Better, let me write E as usual, but this E is not including at the moment the aerodynamic force due to the flexible motion of the aircraft, and these are some imposed aerodynamic force. So these here are external loads of any time. Okay. Stability. We have a very relevant point to fix. In particular, if this is the system in Laplace domain, look at the system in time domain. In time domain, we can transform the equation as in the following: plus kappa q, and here we have minus dynamic pressure, and we can easily apply the convolution theorem so to have a matrix. I want to indicate this strange matrix by capital key. This is a capital key, and this matrix is depending on time, but actually here we have the convolution time and we have the flight speed to be convoluted with the variable q as q time minus tau in d tau plus the external force in time domain. Okay, so what about the meaning of this? Here we have a matrix. We have of course, the mass matrix is m by m model, indicate with the number mode by number mode, again number mode by number mode, and these two are diagonal, and this is also the number of mode by number mode. But what is this? This is the inverse Fourier transform of our aerodynamic force matrix. So T by definition is a matrix of time which is equal to the inverse Fourier Laplace transform of E, function of S and U infinite and time, and excuse me, and stop it. So the point is that we have evaluated the aerodynamic matrix in Laplace domain, on frequency domain, but we could also define the inverse Fourier transform of this matrix, obtaining a time domain matrix. This time domain matrix, time dependent matrix, is obtained inverse transforming each term of the GAF matrix. Okay, and of course, parallelly, this matrix is also function of U infinite. Okay, so we have by definition the inverse transform, and so here we have just applied the convolution theorem. If you have a product, by two Laplace depending quantity, we have by the Borel or convolution theorem that this product in time domain is equal to the convolution integral between the inverse Laplace transform of each term of the product. Okay, and for this reason we have a differential equation in time. Okay, and it is apparent, this dependency. Now we want to discuss the stability, the stability item. Minus, and so here we have equal, excuse me, we have equal. Okay, so what about the stability? in this case, uh, we can determine in such a way Sn and Wn such that determinant of S square m plus k minus qd e s u infinite b equal to 0. So we can solve this equation as an S-depending scalar equation. This is also known as characteristic equation for finding this. And the point is the following. Why do we have to use Sn obtained by this equation for discussing stability? The answer is because the elemental solutions for free response are Q time are equal to W vector by e to the power S and t. And this is not obvious. Note that we have the same question and answer for standard system. And in the standard case, you have x dot equal to ax, and as a Laplace domain counterpart, you have Si minus a, which is the same. Si minus a on an eigenvector, eigenvalues are equal to 0. And the question is answer, is xt equal to W and by ESN elementary solution for the free problem? Question, excuse me, this is the question. The answer is yes, because it satisfies the equation. In fact, if we substitute this solution here, we have W N E S N T dot question, is this equal to A applied to W N E S N T? Take the derivative and you have W and Sn e to the power Snt equal to E Snt A applied to W, and the consequence therefore is A minus identity Sn applied to W n equal to 0. Is this true? Yes, because I have found this constant at this vector just satisfy this equation here. Okay, the loop is closed. Okay, and this is the essential loop, conceptual loop, for accepting that the poles or characteristic exponentials obtained by the solution of an eigenproblem are the elementary quantities for building free response time solution, okay, like this. And therefore any time free solution are a combination of this elementary solution, one for each dimension of the space, for n from 1 to capital N. And this is the generic free response solution structure, as you know. Okay, and this is the logic of system of this type here, and this is the natural connection with an associated eigenproblem. Okay, but this is true also in the case you have system of higher order time derivative. You have just to, for example, another example here. Another important example is the example of mechanical system. You have something like that in mechanical system, second order, but no problem. You have the same logic, and so you have as a parallel problem to be solved the following: S square m plus k w equal to 0. Okay, and in this case, because of the mass and stiffness property, you have poles of type, you have for each n you have a couple pole, for each n you have a couple pole of plus minus j omega n. Okay, and this plus minus is related to the fact that here you have a square. Okay, and this is standard. The same concept are applied here. Okay, and in this case you have as elementary solution exactly the numerical mode of vibration as elementary solution, and you can collect cosine. You can collect cosine for the red case for the solution, and for each cosine you have a couple, number 2 here, a couple of complex solution of type e to the power plus Js j omega n t and plus e to the power minus j omega n t, because you have couple of poles, and for each couple you have a cosine and eigenvector. So this summation is from 1. If you write this summation this way, you have to sum from 1 up to number of n by 2. If these metrics are n by n, you have n. Okay. Now let me write better. We have mode, and here you have to sum on mode. Okay. Okay. So, do we have the same story for the case here? We need a piece for close our loop, our logical loop. We need to demonstrate this. We are not sure at all that a solution like this is a solution of the free response problem. We have to show this. So we have to check the following. Is this solution? Is this not solution? Is this, that's it. Is this, yes, a solution for the free problem given by asterisk. And note that we don't have a simple derivative. We have also an integral with inside the solution. Okay. If yes, so go here. If yes, then one can apply the standard criterion of stability real part of Sn less than 0 stable. Unique solution. And the other case, and Rsn equal to 0, not unique solution. Unstable. Okay, so standard root locus and so on. Of course, we can also distinguish asymptotically stable, simply stable, and so you know this difference. I don't want to say again other concept that you know, but so we have to solve this key point, and for solving this key point we have to simply substitute this solution inside here. So we have m second derivative, we have m second derivative of summation. Consider only one term of the summation. We can just consider the eigenvector by e to the power snt 2 times derived plus k w. So this is the check w and e to the power snt minus, this is the key point, I have dynamic pressure integral from 0 to t, and here we have key matrix evaluated at time tau, and we have to write key in t minus tau. So we have w e to the power t minus tau by Sn. Okay, in d tau. Okay, and of course we are talking about the free problem, so this is 0 for free problem. Well, we have so Sn to the power 2, and here again the exponential m w and plus the exponential, the same exponential, but here we have kappa wn, and again we have qd, we have this integral of this matrix, and here we have tau u infinite, we have this vector, okay, and we have, let me decompose this because it's very interesting to decompose this quantity, and so we have e to the power t Sn and e to the power minus tau Sn equal to 0. Okay, note that we can simplify, of course, this, and we can simplify this because here we have time which is a different time with respect to this here. We commented this point, remember, the day before yesterday, or yesterday probably. T and tau has the same role of x and x star in the boundary integral equation. We have the same variable but independent variable. Same variable, the same problem. This is a time variable, but we have two time variables. The time of the actual time and the time which is useful for the integration. Okay? And so this can be, this can be cancelled. This can be cancelled. Yeah. And at the end, we have, look, we have this time dependent quantity. We have this, we have this in the time, in the tau. And what is this? What is here, this double quantity? Consider that this is the inverse Laplace transform of GAF matrix. And here you have the transform of the inverse Laplace. What is the what is the inverse Laplace transform of the transformed quantity. This is the same story of who is the father of the son of Zebedeo. Chi è il padre del figlio di Zebedeo? È Zebedeo. So if this is the inverse Laplace transform of E, and this is the Laplace transform of T, this quantity here this vector W, which is not depending on time at all. But this quantity is E S U infinite. And therefore, if you take this as free response, if you suppose this to be a free response law, this supposition is correct. Because if you evaluate Sn and Wn as solution of this problem, here, where is it? Of this problem here, then the time solution built in this way is exactly the free response of your problem. Okay, because this quantity has to satisfy this eigenproblem. We have obtained, in fact, this S square m plus k minus qd e Sn u w equal to 0. Yes, this is satisfied. This is equal to 0, and therefore this is the solution. This is a solution of our free response problem, as in the general case of the standard ordinary differential equation. This is valid also for integral differential equation of such a type. Okay, guys, this is one of the important points in elasticity, because we have to justify our generalized eigenproblem. We have, for this reason, we can call this as generalized eigenproblem. Let me write. Okay. This here can be called as generalized eigenproblem. The sense of generalized is intended by the fact that this can be applied also for the case of integral differential equation in time. Okay? Okay. After this key point of this demonstration, we have now the possibility of now evaluate Sn and Wn. Not by assuming a final state approximation for the aerodynamic. In fact, yesterday we underlined the fact that the aerodynamic can be performed by two possible ways. Here, iterative procedure or the path of the approximation of the generalized aerodynamic force matrix. Okay, we have just demonstrated this. Okay, remember this point to be demonstrated. We have demonstrated this. Okay, and we have also already presented this approach. This approach consists of assuming an interpolating structure for the aerodynamic matrix, and after evaluating this interpolating structure, we realize that the system is a system in a standard differential form. And therefore, after this approximation, the theory of the system stability can be developed in a standard way with a standard eigenproblem. But now we don't want to approximate the aerodynamic matrix in this polynomial form. We want to keep this black box as a black box, that's all. And now we want to study the iterative procedure for finding Sn and Wn. Okay? Find this point. Iterative procedure. Let me reload my slides. We have I want to present two kinds of iterative procedure. One, the so-called PK method. The other one is the K method, and that's all. As you realize, the first iterative procedure, the PK method, allows to evaluate poles Sn and eigenvector W and of any type. For any type, I have in mind stable, unstable, and marginally stable. The second method, the K method, allows to evaluate only marginally stable poles. What does we mean? We mean that this is the situation of marginally stable pole. Only this. So only axis crossing situation. Or critical situation. The famous margin of stability. Okay. I want to start with the first method, the PK method. In the PK method, we have some assumption, some hypothesis, but essentially we want to start from our flutter equation. In a general way, we have to solve this. Remember that we are always assuming a diagonal mass and stiffness matrix because we are working with modal coordinate. Okay, we are assuming modal coordinate. So the mass matrix is diagonal, stiffness is diagonal. The aerodynamic matrix is not diagonal at all. Okay, and so we have to solve this equation, and we have our eigenvector W. Okay. Okay. Develop. First of all, we want to separate the complex matrix in the real and imaginary part. So we have a square mass matrix plus applied to W, excuse me, plus K W, and we have minus QD. We have the real part of the matrix applied to W, and again the imaginary part S U infinite applied to W. No approximation up to now. Okay. Next, we have at this point a first approximation. We assume that this real part and this imaginary part are evaluated on the imaginary axis. So we identify this with ER omega almost equal, omega U infinite. In other words, we have that in general, the aerodynamic matrix is depending on S, real part of S, imaginary part of S. And you can evaluate your aerodynamic matrix here, or here, or here. Aerodynamic matrix evaluation. But what you are assuming here is that this evaluation of the aerodynamic matrix is identical to this evaluation. So the real part, the variation of the aerodynamic matrix with respect to the real part of S is negligible. Okay. Of course, this approximation is more and more acceptable whenever your result, your poles are poles close to the imaginary axis. Approximation acceptable if S are close to the imaginary axis. Okay, and of course, by the definition of reduced frequency, this ER is directly function of the reduced frequency. Is assumed to be as directly dependent on the reduced frequency. Okay, so let me stop at 3 o'clock and let's have a break together. Thank you.
Prof, posso fare una domanda? Volevo chiederle se poteva rispiegarmi il ruolo e soprattutto che cosa indica quando abbiamo introdotto nella prima approssimazione della Graph Matrix BM, cioè beta M.
Indica un polo che viene però assunto a nodo della matrice aerodinamica. Piazza assegna come noto un polo alla matrice aerodinamica e lo assegna pari a meno beta. Scusi, lo assegna pari a beta. Ok? Perché un polo? Perché quel numero è il valore di P per cui quel denominatore ho scritto, ho definito nel dominio di Fourier, ho scritto IK, ma se lei lo estende alla Laplace, perché per vedere i poli lei deve necessariamente fare l'estensione della funzione su tutto il piano complesso. Quindi nel momento in cui fa l'estensione jk o ik uguale a p, al denominatore c'è p meno beta, e quindi beta 1, beta 2, beta 3, sono quei valori di p che hanno un loro denominatore, mandando all'infinito la matrice aerodinamica. Quindi sono i poli della matrice aerodinamica. I valori della variabile di Laplace in cui la funzione di trasferimento, la dinamica in questo caso, perde di significato. Vengono assegnati come reali e pari a meno la banda massima del problema per L, diciamo perché c'è una frequenza ridotta, diviso M che vale 1, 2, 3, quindi si prende, faccio rivedere. Allora, ok, allora, vede? se lei qui al posto di iota K si mette, per vedere i poli, per vedere chi sono i poli, uno deve necessariamente mettersi il dominio di Laplace, perché in quel dominio di variabile può determinare dove la funzione di trasferimento, non la funzione di risposta in frequenza, la funzione di trasferimento perde di significato. Allora, questa matrice E di P oramai, quando mette al posto di JKP, ha quel termine che è la somma di, non so, A3 diviso P meno B1. E quando è che si perde significato? Quando P è uguale a B1. Quindi il primo polo sta qua. Da qua, della mia matrice di trasferimento. Il secondo polo sta qua e come li ottiene, diciamo imponendoli, li ottiene lei assegnandoli e come pari a prende un omega massimo. Qual è l'omega massimo? L'omega massimo del suo problema. Quindi la frequenza radiante al secondo, fisica, massima, moltiplicata L diviso infinito, quindi questa è la frequenza ridotta massima. Chiedo scusa che devo rispondere.
Sì, sì.
Lia? Ciao. Sto nella pausa tra una lezione e l'altra, quindi poi... Sì. Lo so, vuoi sapere? Vuoi sapere? Adesso ti rispondo anche oggi su quello, te lo mando, ma vuoi saperlo adesso o poi posso comunicartelo nel pomeriggio? Perché devo parlare con Nasuti e con De Matteis. Con un'ultima cosa. Mm, mm. Sì, lo so. Sì, beh, no, 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 9 è sicuro. Sì, L9 è sicuro. Per una delle due LM20, cioè in particolare per la spaziale astronautica, potevo chiederti di lasciarlo aperto. E quella aeronautica no. LM20 aeronautica no, ma LM20 spaziale astronautica ci abbiamo un margine. Ora Lia, se non costa niente che te lo dico, me lo lasci aperto e poi non lo facciamo, lasciami aperto quello. Esatto, facciamo così. Fai così, Lia, dai, forse è meglio. Brava. Sì, brava, brava. Ok, ok, facciamo così. Ok. Ti posso chiedere poi un'altra cosa, Lia? Perché, oppure magari ne parliamo dopo. Era relativamente ai bandi dei percorsi di eccellenza che stavo sistemando. No, non adesso, ok, va bene, ti chiamo dopo. Dopo le 4 sei disponibile? Allora ti chiamo dopo, dai, meglio. Grazie. Ciao Lia, ciao ciao. Quindi le dicevo, questa è una tecnica in cui i poli si assegnano e quindi non bisogna cercarli nel processo di least square per la determinazione della forma interpolante. Va bene?
Ok, ok, va bene.
Mm? E quindi quando uno andrà a minimizzare l'errore tra i dati aerodinamici e questa struttura interpolante e cercherà come incognite interpolanti solamente le matrici queste in rosso, mentre nell'altra forma, questa qua, in cui le matrici erano indicate incognite, stavolta erano indicate in nero, tra le matrici in nero c'è anche una specie di denominatore che è questo P, è una specie di beta, un po' meglio di quel beta, addirittura è un'intera matrice che fa da denominatore. Quindi anche in questo caso ci saranno dei valori di jk, meglio di p piccolo, che faranno in modo di annullare non quel denominatore, il determinante di quel denominatore matriciale, sì, saranno proprio i valori di quel p piccolo saranno proprio gli autovalori di p, dicevamo ieri. Anzi, come hanno detto alcuni di voi. Va bene? E questo è. Ma ora stiamo facendo un'altra cosa. Ora stiamo dicendo, rinunciamo a questo processo di fitting dell'aerodinamica, che nella teoria analitica di Todorsen è diventato un processo di fitting della funzione di Dodorsen, perché anche lei è trascendente, e anche lei la possiamo pensare come una frazione polinomiale nella variabile di Laplace P. Si fa, e anche per lei troviamo dei coefficienti che ne fissano la struttura, sempre trovabili con un processo di minimi quadrati, di errore minimo. E vengono questi numeri. Ecco, anche qui, se si assume questa struttura per la matrice C, allora questo equivale a assegnare uno stato aerodinamico aggiuntivo unico, una variabile aerodinamica unica, che qui forse ho fatto confusione nel chiamare anche questa beta. Questa beta è una beta di T, una beta di S, è una variabile di stato. E chiamo con beta non proprio tutta quanta quella roba che ho cerchiato in rosso, ma la roba che ho cerchiato in rosso, avendo però preso solamente la parte propria di C, ho precisato ieri, così come ho preso la parte propria di quella frazione precedentemente per definire lo stato aerodinamico aggiunto nella teoria generale. Ecco, con tutte queste cose si arriva poi, facendo una fatica iniziale, a fare meno fatica dopo nello discutere la stabilità, perché la stabilità diventa standard, diventa un problema di autovalori standard. Adesso sappiamo, questa era la superficie importante che abbiamo fatto ieri, la stabilità diventa standard. Ora siamo tornati indietro oggi, abbiamo detto no, adesso rinunciamo alla stabilità standard, facciamo la stabilità senza interpolazioni dell'aerodinamica, no, così com'è. Questo così com'è è così com'è Nastran, per esempio. Nastran usa questi approcci qua. Quindi abbiamo deciso di considerare tutto il problema prendendo l'aerodinamica come scatola diciamo, nera, chiusa, che ci fornisce per ogni valore di S un valore della matrice aerodinamica. E senza andare lì a fare interpolazioni, no, lasciamo perdere. Quindi abbiamo questa equazione di Flutter da risolvere nel problema libero, generalizzato. Ma ci devo credere che i poli che ottengo scrivendo determinante uguale a 0 sono le cose giuste da studiare come criterio per la stabilità? Beh, il ci devo credere è legato a questo ci devo credere. Nei sistemi standard, puramente differenziali, il ci devo credere è facile da dimostrare, perché se io assumo avere risposte libere di questo tipo, queste soddisfano l'equazione, l'ho visto qua, solamente se è vera questa, ma questa è vera, perché è proprio la relazione che ho utilizzato per trovare S/W. E quindi queste sono le soluzioni elementari del problema libero. E quante sono? Beh, quanti sono gli indipendenti W? Ce li metto tutti. Per un problema n, la matrice di stato di dimensione n, cioè n autovettori, ci metto tutti gli n autovettori combinati tra di loro. E questa è la generale struttura del problema libero, che si discute, è convergente, è stabile la risposta solamente se S con n sono parte reale negativa. Ma questo pezzo bisogna dimostrarlo nel caso del problema dell'elasticità, perché non è mica detto, che ne so, che quelli che ottengo attraverso il problema di autovalore generalizzato sono poli che posso trattare alla stessa stregua. L'abbiamo fatto vedere, perché abbiamo preso quella struttura di soluzione, l'abbiamo messa dentro l'equazione del problema libero, che è questa è l'equazione del problema libero, uguale a 0, e abbiamo visto che questa equazione è soddisfatta, vedendo che qui c'è di fatto una trasformata, scusa, di questa chi che era l'antitrasformata di E, abbiamo visto che questo è vero solamente se è vera questa. Così come prima avevo detto, guarda, questo è vero solamente se è vero questo, ma questo è il problema di valori che l'ha generato, e qui è la stessa cosa. Questa è vera solamente se è vera questa rossa qui, ma questo è proprio il problema di autovalore generalizzato che ha generato S con n e W n, e allora niente, anche in questo caso quella lì è la struttura di soluzione. Anche in questo caso, pur essendoci la matrice aerodinamica che complica la vita, eccetera, trovando quelle costanti in quel modo, con quelle costanti si può discutere la stabilità. Punto. E questo è una buona fetta del corso dell'elasticità. Solamente per capire questo uno ci mette diverse settimane, mettendo in ballo...
Prof, allora la domanda è per quale motivo, anziché utilizzare l'approssimazione che abbiamo visto prima, che quindi con un po' di fatica però si arriva a un sistema standard da analizzare, Nastran utilizza un modello iterativo come quello che che stiamo facendo adesso?
Perché te la sei data lo stesso tu la risposta, perché quella è un'approssimazione.
Beh, sì, ok, sì.
Perché quella è un'approssimazione,
Effettivamente.
perché quello approssima un qualche cosa che dovrebbe avere infiniti stati con un numero finito di stati, finiti stati nel tempo, con un numero finito di stati.
Quindi non è, cioè nel senso, ok, è un'approssimazione, però quindi non ha un livello di accuratezza abbastanza elevato?
Potrebbe non avere un livello di accuratezza abbastanza soddisfacente, anche perché tu poi ti trovi a dover decidere tu se l'approssimazione dei dati della matrice aerodinamica è soddisfacente, no? Attraverso
Certo.
il processo di fitting. E si usano queste cose perché io so di certo che si usano. Io vi posso far vedere anche dei risultati fatti su velivoli attualmente che volano, di analisi di stabilità fatta col metodo con gli stati finiti, non c'è problema. Però richiede forse una maggiore cura e tutte le cose che richiedono manutenzione e cura, anche quello è lavoro impiegato, è lavoro non dico sprecato, ma è lavoro impiegato pure quello. Okay? Quindi uno si tiene tutte le possibilità, poi scegli. Quello che stiamo vedendo adesso è un metodo a punto unito della serie dei metodi a punto unito o continuation method che si usano per risolvere questi problemi non lineari di equazioni caratteristiche che non sono polinomi. Di fatto il problema è un'equazione caratteristica che non è un polinomio. Attenzione, non ho mai parlato della determinazione di W, ma la determinazione di W è sempre la stessa, è sempre un problema omogeneo, perché tu devi prendere Sn, la metti dentro, l'hai trovata, hai trovato il tuo valore, lo metti dentro e quella matrice diventa, perché l'ha chiesto te, singolare, e allora devi trovare l'autosoluzione di una matrice singolare. E quindi sempre l'autosoluzione di una matrice singolare è la determinazione di W, sia che fate sia se fate con l'interpolazione, sia se fate con i metodi iterativi. Cioè, il problema dell'autovettore non cambia, è sempre quello. La differenza sta nel determinare gli autovalori qua.
Mm.
Ok?
Ok.
Okay. Let's go. And okay. So we have this with this PK method. We have to solve this generalized eigenproblem. So determining this Sn and this eigenvector, but the problem of the eigenvector is trivial because it's just a problem for finding the eigensolution of a matrix which is singular, okay? Because when you put inside here a root, a found root Sn, this matrix, all this matrix here is singular, and then the only you have not trivial solution, not zero solution, and this not zero solution vector is your eigenvector itself. Okay, so first approximation of this procedure, we want to substitute here not the value of excuse me, let me take the glasses. Not the value of the actual value of E as a function of S, but E as a function of omega, or E as a function of K, the diffuse frequency set here. This is an approximation, of course. This approximation is susceptible if S, all the poles are close to the imaginary axis. So whenever this real part is higher and higher, and lower is the level approximation of this method. Okay. Okay. So we have, after this position, we have S square M. We have W N plus K W N, and for the imaginary part here, we have this is the real, this is the imaginary. Excuse me, this is imaginary. We have a J because you have the imaginary part. Yes, of course, you have E equal to real part plus J imaginary part. Okay, so we have this J here for the imaginary part. And so you have minus QD, the real part. At this point, the real part is depending on K, and we have minus Q D J, and we can multiply and divide this quantity by S function of K, and we want to divide by S. So we have multiplied and divided by S, and for this S here, we assume the same approximation we did for EI, and so for this we write JK, same approximation, by W, and this is equal to 0. So at the end we have the following: our flutter equation becomes S square M W plus K W minus dynamic pressure, real part K W minus, and here we can simplify this and this, and we have d Kd by S imaginary part and divided by K, 1 on K W. So AI is a function of K as is divided by K, okay? Wn equal to 0. Note that by assuming this position here, we are separating the destiny of S with the destiny of K. But in reality, S and K are related, but we have unrelated this dependency. So giving to ER and EI and a dependency on K, which is at this level independent by S. And this is a strategy of any kind of continuation method, or punto unito in Italiano. Okay. In fact, I want to open your mind with all the problems you face in your life. For example, you have to solve this equation. You have to solve this equation. You have to solve this algebraic equation. For example, x cube plus 3x minus to the power 2 minus logarithm of x plus x equal to 0. This is an fx equal to 0, okay? When you apply the continuation technique, you want to isolate one x by this expression, for example, this x here, and you want to rewrite this like x equal to phi of x. And here you have x is equal to minus x cubed minus 3x cubed plus logarithm of x. And you iterate as the following. Look, you iterate in this way. X n plus 1 equal to phi in xn. So here, imposing this, you have separation of the destiny of the root. You have two separated values for x in the iteration n and x in the iteration n plus 1, and you are expecting that these two values are distinct. And when you converge, x in a step is equal to x in the next step. This is the continuation approach. This is the punto unito. So here we are initially assuming that K and S are two uncorrelated quantities. And you want to play the role of K for your scope. Okay? Okay. This is the deep meaning of this approach. At this level here, now we are ready for rewrite our equation in a suitable way. In particular, look, now we have the following. We have S square m w plus k w and minus qd e r function of k w and minus qd ei k w n by k divided by k and multiplied by s is equal to 0. So in this method, the real part after this position for the continuation method, the real part is assumed as a stiffness part, and the imaginary part divided by k is a stiffness part, because a damping part, excuse me, because you have s here. Okay, excuse me, let me put in evidence in a more suitable way. We have this this okay, as a damping, and this is a stiffness. This means that we want to group a mass term a stiffness term like minus d s excuse me, function of k by k w. And then we have also a stiffness term grouping the real stiffness matrix and this real part of the aerodynamic matrix. Again, this stiffness term is applied to W equal to 0. Note that all the matrix are real matrix. This is a real matrix. This is a real matrix. And this is a real matrix. But of course, the aerodynamic matrix are all depending, are at the moment are depending on K. Okay, so we can move to a standard state space for in particular, we can define the product S by W like a V vector, complex vector, and therefore we have S M V vector. Indeed, here we have S square V, so instead of S square V, we write SV minus or equal to, directly equal to plus QD EI K vector on K SW is V. And finally, minus kappa minus 2D E kappa on W. And now we can pre-multiply the second equation by m to the power minus 1 minus 1 minus 1. And so we have a standard, yes, we have the following standard form. We have S multiplied by a unique vector like W and V and is equal to a matrix. In this part of this matrix, I have to consider the first equation. The first equation, I have V, and therefore here we have 0 and I identity. In the second, in this partition, this and this, we have here we have V and W. So first W, and so in this W position, here we have a minus sign. Do not confusion, please. This is a minus sign. And so we have the part multiplying W is minus M to the minus 1, K minus QD E real. This was the real part. Real part function of K, and in the other part we have the part multiplied by V, which is plus QD M to the power minus 1, and we have EI, imaginary part, divided by kappa, kappa in black, because I want to emphasize the point. So I have kappa, and I have kappa here. And so this is the result. I have the following eigenproblem: S U equal to A U. So we can solve this problem. But what is the point? Attention, please. A is a function of kappa. It's a parametric dependency on kappa. And do not forget the fact that kappa and S in the reality are not uncorrelated, not at all. Not at all. Because if you take the imaginary part of S, and multiply this imaginary part by L and divide by U infinity, you should have kappa. So remember, remember that the imaginary part of Sn evaluated in a standard way divided by U infinite and multiplied by a reference let like L, this quantity should be kappa. And this is the closure of your iteration procedure. This is the closure of your punto unito or continuation point. Here we are assume this, but at the end, so here we assume that the destiny of x in the right hand side is different by the destiny of x in the left hand side, but these are practically the same x. And I want to ensure this point and yet at the end of my discussion. So this is the point of my iteration point of my iteration procedure. My iteration procedure is the following, and I want to conclude my comment on this K method, on this PK method. I have the following scheme. Fix the flight parameter in my linear theory, unsteady, uncompressible flow, the flight parameters are rho, altitude, the density of air, and U infinite. Later, we will have also Mach number, but not at this level, not at this point. So fix your flight parameter. Then you can fix, first of all, evaluate the evenience, occurrence, better, the occurrence of divergence. Zero pole. And this is a preliminary test. So you have just to put k equal to 0. And so evaluate your eigenproblem with A for k equal to 0 minus Sni un, and solve for S1, S2. Is any of this 0? R is 1. Is any of this 0? If yes, you have this parameter as divergence parameter. You are in divergence condition. If for the k assumed, in this case k equal to 0, you have that this problem is giving to you a 0 eigenvalues, then you are in divergence condition. Then U infinite is a divergence velocity. Your density value is a divergence density value. You are on divergence. Okay? This is the first check, Second check, and here you have a loop on kappa. Assume kappa, an initial guess, 0 initial guess, for a kappa useful for finding your first poles. So assume, guess, then evaluate the space-based matrix A as given for this value of kappa, and then evaluate the first value or the eigenvalues associated to this guess, initial guess, to this initial guess. So you have S1, S2, S3, and Sn is associated to this guess. Okay, the very standard situation for starting is the first structure pole. If you have an omega-1 structure pole, suppose that this is the structure pole, J omega-1, and you have a complex conjugated here, minus J omega-1. And the point is that suppose that this is the aeroelastic pole. So the initial guess for the aeroelastic pole searching is the structure pole. So typically one use for this omega-1 L by U infinite, this U infinite. Okay, so assign this K such that the corresponding omega is the frequency of vibration of the irradiant of your structures. Okay, so this is the natural frequency of the structures without aerodynamic, and you want to search the poles including the aerodynamic. So evaluate K, evaluate AK, and so evaluate this quantity by solving A K01 minus S0 I U, and find this S. Then check, what about the imaginary part of your evaluated S01 by L divided by U infinite? Is this quantity greater, equal, or less than your initial guess? Better, ask directly if this is equal to, if this is equal to this. No. Then next step, the new K1 tentative is equal to the imaginary part of S0 1 L divided by U infinite is here. And then evaluate A at K1 1, evaluate the eigenvalues, and u. And so this is the first tentative, zero. This is the next one. We are moving toward the correct route. In this case, you ask, is the imaginary part of the new evaluated S1 1 L by U infinite B equal to the previous one, K1 1? Yes. If no, again, iterate. And you have an iteration here. At the end of this iteration, you have, when you say yes, you say that S1, the first pole, is equal to, is such that the imaginary part of this S1 by L divided by U infinite is equal to the convergent kappa. And so from this initial guess, we are here in our elastic pole, because at the end of this iteration, you have satisfied your flutter equation, and you have satisfied the condition that the pole you have reached is such that the imaginary part by L divided by U infinite is exactly equal to the value you have put in input for the aerodynamic matrix. Okay? And this is done for the first pole number 1. Then you can do the same iteration for the pole number 2. So using as initial guess number 2, if this is the second mode of vibration, and you are looking for this aeroelastic pole, you use as initial guess again the natural frequency, the second natural frequency by L divided by U infinite. Initial guess. And then iterate with the same step. And so okay, and so this is the PK method. You can do this for any set of flight parameter. So at the end, after an iteration for a given set of U infinite and rho infinite, you have your pole like this, this, and this, and you have also the you have also the symmetric one, of course, SR and SI. If you, for example, fix the altitude and you variate U infinite from two values, from 100 meters per second and 115 meter per second, you have a root locus like this. You have this, for example, and you have this, for example, and you have this, for example. And this is the flutter condition. What about a comment about this result? If you obtain this result, you know very well that the pole evaluation is coarser and coarser whenever your real part is increasing, because remember that we have supposed this condition here. We assume that we are separating the destiny of S and K, yes, and the approximation is acceptable if the poles are close to imaginary axis. So this is the approximation. This and this. The function of S, function of omega, function of S, function of omega. Okay. And this is the PK method. The name of PK is the following. In the 17, when this method was introduced, oh my God. Okay. When this method was introduced in the 17, PK, the role of P was the Laplace variable. And K is the reduced frequency. And the method is called PK because it's based on the interpretation of the Laplace. So in our case, after many years, we called the Laplace variable by S, and we call with P the undimensional Laplace variable. So the actual name to be given to this method today should be SK method, because we used and we separated the role of the S with the role of K. But in the reality, at the end of the loop, S and K are heavily related. Okay? And this method is also known as British method. Okay? Typically, the result of the stability are presented by root locus of the velocity, but are also presented with this plot here, with the u infinite in the axis, in the x-axis, and on the y-axis, the real part of the eigenvalues and the imaginary part of the eigenvalues, which is omega. If you multiply this omega by 2 pi, you divide this omega by 2 pi, you have the frequency. And this is actually the damping. So you have some result like this. You have a negative damping, negative real part, and then you have this. And this is the flutter velocity. And you have also the frequency varying in this way because of the flutter velocity. Okay, so this is the first pole. And you have several curves for any pole like this. Second one, third one. So first, second, and third. Okay? You have the frequency variating and the frequency variating with the velocity. So this curve is also known as VG plot because the damping is also named like G. Okay? Okay, stop here. So we have finished the modeling of structure and aerodynamic. We are studying at the moment solution. The solution of the elasticity and the solution of the elasticity are faced with the evaluation of stability and response. Okay? See you next week. I want to, how many of you are familiar with Nastran? Better. Is anybody not familiar with Nastran? Anybody?
Yes, Professor.
So I would like to share with you Nastran model of a section of a wing, and I have in mind to propose to you a structural and flutter stability analysis. And so next week I begin to show you an Nastran model. You should to provide a student version for perform our analysis in the exercise number 2 and exercise number 3 and number 4, which are the last two exercises in this course. Okay, so I address to you this facility, this code for allowing to you the exercise number 3 and 4. Again, thank you for your attention and see you this Monday.
Mi scusi, io se non sbaglio avrei un problema con Nastran perché la licenza scadeva a novembre, se non erro. La licenza aveva un termine novembre 2020.
Guardi, se lei è iscritto non scade niente, se lei è iscritto se è scaduta rifà l'applicazione, come studente Sapienza gliene danno un'altra.
Come funzionava, professore? Che non ricordo dove l'avevamo...
mscsoftware.com.
Ah, ok, mandavo la mail, era così.
Cerca sul sito, non deve mandare cerca sul sito e c'è scritto come si fa. Deve fare un'application, deve fare una richiesta come studente con il tesserino Sapienza.
Ah, ok. Ah, sì, mi ricordo. Sì, giusto.
Ok?
Ok, perfetto, grazie. Buon weekend.
E questo per chiunque altro abbia bisogno di questo.